Hello everyone, welcome back to another video. And today's video, I finally have a brand new whiteboard, guys. And today's video, we are going to be exploring I'm going to be proving the argument of complex numbers. But first, I just want to show how good the whiteboard is. So basically, this is the big whiteboard, okay? But I want to do the complex plane this month because I want to see if I can write some extra stuff here. So that's why, okay? So first, so let's just get into today's video, okay? So in today's video, I'm going to be proving the argument of a complex number and the polar. So first, let's start with the argument, okay? So look, in this, you see these quadrants? So the quadrants, so these quadrants, look, these are known as quadrants. Basically, look, these are the quadrants, okay? A quadrant is something like A and B are from A plus BI. And in this case, A and B, this is what they're representing in this, okay? So that's basically what's going on here. That's basically the quadrant, okay? So So now that we know about the quadrant, look, in simple words, the quadrant just tells what sign A and B are in the complex number form, okay? So I'll just give a quick example. For example, if we have a complex number in the form, let's say, sometimes we have something like minus 5 plus 3i. Okay, so in this case, minus 5 is negative, so it's less than 0. And in this case, b is greater than 0, so it's positive. So that's why it belongs to quadrant 2. Okay, these are the quadrant. This is quadrant 2, this is quadrant 1, this is quadrant 3, and this is quadrant 4. Okay, and they each tell the sign of the numbers in the complex number. Okay, form. Okay, so just want to give you a little understanding of that. Okay, so now let's begin. And look, the reason I'm drawing this argument, the reason I'm putting these quadrants is because each argument in different, the arguments are different in each quadrant. Okay, so look, first let's define argument. So look, what is we can say? Let's understand what an argument means. Okay, argument. Okay, so look, determining what angle a complex number represents on the positive real axis. Okay, now look, you might be wondering that why do we have positive? Now this is important to know, because the argument means that the reason we're doing positive is because usually angles like positive angles are more accepted than negative angles. See, negative angles exist, but because this is like the standard way, this is like the standard side to represent angles, okay? Positive real axis, okay? So just up to here, just understand that, okay? And now, because first you should know what the argument means, okay? Okay, good. Now, let's move on to our next topic, proving the argument. Okay? What the hell just happened? My blue marker. Oh, damn it. Okay, I'll just use a different one, okay? So, first, in order to prove the argument, let's just plot any complex number, okay? What do you say? 3 plus 4i? Okay. Let's plot 3 plus 4i, okay? So look, 3 plus 4i. This is 3, this is 4i. Okay? This is the point. And remember, what quadrant? This is in quadrant 1, where A and B are both greater than 0. Okay? So look, this is the point this is 3 plus 4i. Okay? Now look, this is how to plot generally, but I'm going somewhere with this, okay? Just trust me. Look, what you have to do is just extend a line, and this is not the scale, but I'm just making it as accurate as possible. First, draw a line from the imaginary point to the point, and then from the real point to this point. Okay? Clear to here? Now, what we want to do is, we're going to draw a line like this, horizontally, from 4i to 3, like this. Okay? Now, it's not the accurate way. I think let me just make it a little more accurate. Okay, good. So look, what this is basically, this is a right angle triangle. Okay? And what's happening here? It doesn't look like it, but it is a right angle triangle. Look, this is the base. This is the base. This is the base. Okay? This is the perpendicular line, and this is the hypotenuse, okay? So what you're going with this is that the reason I'm drawing this triangle is because when we plot this complex number, this right angle triangle helps us to see the argument. And one more thing, I'm also going to prove the modulus of a complex number, which is the distance of it from 0, but in this case, I'm going to focus on the argument, okay? So first, the argument angle will lie on the hypotenuse, okay, like here. Okay, now first, let's call it theta, okay? Let's call the argument theta. This is theta, okay? So we don't know what theta is yet, okay? So first, we can use trigonometry here. Look, we know that we can call this tan, right? Because in trigonometry, the hypotenuse is also known as a tangent. And we know that tangent is equal to the opposite. We can just call this opposite also. Opposite over adjacent, yes. So tangent, the tan of theta is equal to the opposite side over the adjacent side. Okay? So basically, like there's also, and also we can also call the opposite angle sine, right? Sine. And we can also call this cos of theta. Right? But for now, we don't have to worry about sine and cos right now. For now, we're just going to worry about the opposite side and the adjacent side, okay? So look, when you want to figure out what theta is, we first have to remember a formula. Tan of theta is equal to the opposite over adjacent. Yes. This is the formula, okay? And this is a very important formula because this helps us to find the argument. And look, in this case, the opposite side is b is equal to b. We can simplify this as b over a, because b is the imaginary part of the coefficient of I, and a is the real part of the complex number. And in this case, we have to put the coordinate points. So the points of this complex number are 3, 4, right? A, B. Yes? This is the points, 3, 4. So we have to put the points, B over A. Okay? Now what is B? But we have to flip it up. Why? Because in this case, the opposite is on this imaginary side, and the adjacent is on the real side. Okay? Adjacent. Alright? So we can see here that the point's 3, 4, but the thing is, the tangent is B over A. So B over, what is B? B right here is 4. So this will be 4. Okay, 4 upon a. And what is a? 3. And this is how you find. Now look, we're not done yet. We're not done. We're not done, okay? Alright, so first, let me just clear some space here. Okay, look. So now coming down here, I'll just bring you down here. Alright. So look, let's bring this down. Okay, look. Now what do we have? We have tan theta is equal to 4 upon 3. But we're not done yet. Our goal was to find theta, right? So we're going to find theta. And how do we do that? We have to transpose. Or what we can do is, we can divide tan on both sides. So this will cancel. And we get that theta is equal to tan to the minus 1 of 4 upon 3. And this theta is known as the argument of the complex number. Okay? So this is how to find it. And more specifically, this is known as the argument of which complex number? 3, yes, 3 plus 4i. Understood? Okay, understood? We'll go with more examples. Now this was just with quadrant 1, where a and b are greater than 0. But this is not the same this. No. So the general formula is yes. Is that the argument of a complex number is equal to tan minus 1 of b over a. This is the general formula. But this is only for so the argument of a complex number will be tan to the negative 1 of b over a only for which quadrants? Quadrant 1, and the other quadrant is quadrant 4. Okay? And you'll see why it's not for quadrant 2 and 3 in a bit. Okay? Because quadrants 2 and 3 are different. So now let's show that. Okay? So let's clear the space. So I hope you understood till now. So this is how to find it, okay? And the sine cos will come later, then find the polar form, okay? So now, coming to the next quadrant. Okay, so look. Now we have found, so now I'm just going to write here that tan, that argument of 3 plus 4i is equal to tan to negative 1 of 4 upon 3. Okay? Well, let me just write that a little clearer. So the argument of 3 plus 4i is equal to tan to negative 1 of 4 upon 3. Okay? Just remember this. And this is an example. So the general formula we can derive from this is what? Yeah, the general formula we can derive from this is the argument of z is equal to tan to the negative 1 of b over a. Okay? But this only works for these two quadrants, 1 and 4. Okay? Understood to understood? Okay? I hope everything's clear till now. Okay? So now that we finished this part, let's move on to the next, okay? To the next quadrant. Quadrant 2. Now for this, I'm going to use a green marker, okay? Because the argument is different. And I'm going to explain why, okay? So look, just give me any complex number, okay? Because in this case, a is less than 0. So b is greater than 0. Okay, let's take minus 4 plus 4i. Right here. Okay? This is negative 4 negative 4 plus 4i. This is the point. Okay? This is the example I'm taking, okay? Negative 4 plus 4i, okay? And now, once again, like we did in the last example, we're going to have to join the points. 4i here, this is not to scale, so make it as accurate as possible, okay? And then, but just pretend this is a straight line, okay? Okay, look, so this is a straight line, okay? We're connecting 4i to the point. Now, same with negative 4. We're going to connect negative 4 to this point, okay? Clear to here? Clear? Okay? So now that we connected the points, let's join them, okay? We're going to make it'll be like a little triangle shape, like the hypotenuse. Oh, that's not so cool. I'll just turn it here. So when we join this, we're going to get a hypotenuse. Yeah, that's true. So we're going to get a hypotenuse like this. Okay, all good? All clear to you? Yeah, so what happened is, when we join these points, we join this point and this point. Okay? Negative 4 and 4. Now what happened is, when the point is here, okay, we're joining these 2 points. And then we have to join them once again by creating the horizontal line like this. Okay? Now look, this once again is the hypotenuse. This is the hypotenuse, okay? And this hypotenuse, and the argument, where will it lie? Now look, the argument here will lie somewhere like here. One second. The green mark was here, right? I shouldn't draw that. I should just draw it here. Yeah. Like this. So now it looks like a triangle. Okay, good. So now the argument will lie here. Next towards the hypotenuse, okay? So look, it'll lie here. But for now, we're gonna call this theta. Because we don't know what theta is yet. Okay? So this is what we created. The same with the last example. Okay? That's how it is. Because you have to determine the longer side, okay? The longer side. The longer side. Okay? And this is the hypotenuse, which is the longest side, and the right angle triangle. Okay? Now look. So same concept. What we're going to do is we're going to use tan. Use tan here. Okay? Let's just bring it down here so it's easy. So in this case, we have tan, and this is also known as tan. Yes. Hypotenuse. We're going to see. So this will be tan of theta. Tan of theta. Okay, tan of theta is equal to. So we already derived from the last formula, so we're just going to use that. Is opposite over adjacent. Okay? Or we can say that B over A, as it derived in the last example. Okay? So we have the tan of theta is equal to B over A, okay? Now look here. Now we have, what is B here? B right here is, let's plug in the values here. Okay? Okay, so the values are here. B is equal to negative 4. No. Sorry, B is equal to 4. Okay? And A is equal to negative 4. But we could just shift the negative sign up here. So, for simplicity, you can just rewrite this as negative 4 upon 4. Okay? Which would be, this would come out to be negative 1. But look, there's a problem right here. And you know what the problem is? The problem is that, let's see, this is a negative. Okay, first, let's just understand it clearly. So look, we have a negative number. A is less than 0, okay? It doesn't matter if B is greater than or equal to or less than 0. So what's happening is, we have a negative number. But the problem here is that this is a negative number. But look, doesn't this look familiar? Like the argument of this, like for example, look at quadrant 3. And here, look, yeah. Because, look at quadrant 3 for a second. If you go to quadrant 3, we can find a complex number here. We can find a complex number, like, we can find here -4 minus 4i. Okay? And in this way, the a and the a are equal, right? In the sign. Okay? So look. Like the thing is, okay, first let's simplify this. We're gonna get -1. Okay, -1, please. Now we get that tan of theta is equal to -1. Before I go this, I also want to this is the opposite. This is the opposite. And this is the edges. Okay? Now let's go back to this. This is the equation. The problem is we get tan of theta is equal to -1. Now let's divide tan by both sides. Okay? Let's just make space here. Let's erase this just to make some space. Okay? Now coming back to the equation. Tan will cancel. And we get that theta, which is the argument, is equal to, is equal to tan of -1 of -1. Yeah, so like, okay, let's read it. Let me bring this. Divide by tan. Divide by tan. Times tan of 1. Yeah, so tan of -1 of -1. We get this. But you might think, oh, this is okay. We just have tan raised to the power of -1 and of -1. And you might be thinking, oh, there's nothing wrong with that, right? But look, the problem is when you're taking, this might look familiar, because in this, we're taking tan of -1. In this example, quadrant 3, a and b are less than 0. So if we found the argument in this side, like in quadrant 3, suppose I take this, so tan of theta will be the opposite, so the imaginary part over the real part, so the imaginary part or real part, and this will be -4 upon -4. But this will be 1. But the problem with this, as I'll explain later, that this is also equal to the argument of 4 plus 4i, which is a problem. And in this case, the thing is, we're going to have to add pi to the argument. Okay? What I'm going to do is, we're going to have to add pi. Let me explain what I mean. No, I mean, yeah, you should add pi. But I think it would be better if you had pi to start. So we actually have to have pi plus the modulus of tan -1 on this. I might be thinking, wait, why are we taking the modulus? We'll take a look. In this case, tan of -1, if you take the modulus, we get a positive result. Now, in order to convert this into radians, we can see that. Now, but if you want to convert this into radians, we need a calculator for that. But obviously, we don't have one, so we're not going to focus on that. But the main point is, when we have an actual value symbol right here, we take tan of the -1 of -1. So when you take that, it'll be a positive result. If you don't get it, it'll be a negative result, right? And if you get a negative result, look, when we add pi, look, pi right here. Now you remember one thing, 90 degrees is equal to pi over 2 radians. Remember this? So when we multiply 2 by both sides, we get that 180 degrees. We get that 180 degrees is equal to pi radians. So what happens is, as I told you, that in my community post, that the standard way to express the argument is in radians. So that's why we don't have to add any unit after pi. That's the thing. It's because it's already known. And look, what happens is, let's do example. Pi. You know what happens is when we add, we're adding 180 degrees. Do you notice this? So what you first do is to understand, you have to convert to degrees. 180 degrees. And remember when you rotate by 180 degrees, the sign changes. And because what you're doing is, we're shifting the quadrant. What I mean is, because if we didn't add pi or use the modulus, we would land on the wrong quadrant, which would give us the wrong argument. That's the thing. Because tan of the negative one, no, you'll get a positive result. This will give a positive result. And when you rotate this by 180 degrees, it'll turn into a negative result. Because that's what we want. We want a negative result. Because in this case, the argument would be, it would be less than 0. Like in radians, it would be less than 0. Because in this case, A is less than 0. But B is fine, it's greater than 0, so the result will be negative. But the problem is, the tan and negative, look, if you so the tan and negative 1 is equal to what? Pi over 2, right? So, yeah. So that's the thing. We're shifting the quadrant. Okay, understood? One more thing. I have to explain the range. Because the thing is, you have this tan. One more thing. The tan function, the tan formula. Look, the formula tan to the negative 1 of b over a works only in quadrants 1 and 4. 1 and 4. Because they're both positive. Where a is greater than 0. Okay? So that's why. Because the thing is, this only works if a is greater than 0. And when a is less than 0, we get a negative angle. And we don't want negative angles. So what we do is we have to take the mod and then we have to rotate it by 180 degrees to make the result negative. Okay? So that's why we're adding this pi. Okay? Understood? Okay guys, so I hope you understood this. And look, and one more thing, I have to mention that the tan thing actually, what happens is the tan function, so where's this? The tan function, okay, the tan function works in the principal range of like works in the range of negative pi to pi, right? So that's the thing, because in this case, look at this side, okay? So then in the range will be negative, so like this means negative 180 degrees 180 degrees. Okay, that's the thing. Because in this case, look, what this will work. The tan function will work between the range of negative pi and pi in radians. This in radians. In radians. But yes, this is in degrees. Okay, and the thing, you don't have to put a modulus for quadrants 1 and 4. Okay, just remember that. Okay, so that's the thing. Now let's move on to quadrant. So first, let's derive the formula. And look, and actually, we can also subtract. Yeah, because when we rotate 180 degrees, and it's the same thing as we're rotating minus 180 degrees. Like if you have 4, if you rotate 180 degrees, then have negative 4. But if you rotate negative 180 degrees, it'll still be negative 4. Understood? So the rotating 180 degrees and negative 180 degrees give the same rotation. So that's why it'll be pi plus or minus the modulus of tan of negative 1 of negative 1. Okay? You guys, one more thing, I have to fix something actually. The tan function only works in the range of actually 90 degrees. So pi upon 2 radians. And up to pi upon 2. So this should actually be from 90 degrees, negative 90 degrees to 90 degrees. Okay, understood? And look, we don't have to add negative because it doesn't really matter, so we can just add pi to rotate in 180 degrees, okay? Because the thing is, from negative 9, from 0 to, look, in this range, from like negative 9 to 90 degrees, the tan function will be the tan function will be positive, but it will be positive, right? Let me get a marker. But the thing is, when it moves from 90 degrees to 180 degrees, it becomes negative. It decreases. So this is increase. This is an increase. This is an increase. Okay? And then we move from 90 degrees to 180 degrees. The tan function, it will slowly decrease. It will go down. It will be negative. Okay? And that's the thing here. In this case, A is less than 0. And it will be outside of this range. It will be outside of this range. Because when we go from 180 degrees rotation from this 180 degrees, it will decrease the tan function. Alright? Understood? So that's the thing we're talking about. So let's just draw the general formula here. Yeah. So it only works in the range of pi upon 2, from negative pi upon 2 radians to pi upon 2 radians. Okay? Alright? Understood? Okay, so now that we've done this, let's draw the general formula here. We'll get that tan. We'll get that the argument. The argument will be tan. Will be pi plus tan to negative 1 of b over a. Okay? That's how we get it. Because actually the modulus, yes. We put the modulus, okay, to ensure a positive value for them. And one more thing, guys, tan to the negative 1 of negative 1 is actually negative 45 degrees. If you check on the calculator, it will be negative degree. But remember the definition of the argument? Determining what angle a complex number represents on the positive real axis. This is negative. That's another reason, okay? Just another that. If you have any confusion, you can let me know. Okay? So look, that's what's happening here. We have to first put the modulus, and then like pi. In this case, we have pi plus tan to negative 1 of negative 1. Okay? Now when we add pi plus the modulus of 5 degrees, this will become pi plus 45 degrees. So, yeah. Actually, we don't want this in radians. No, so you can convert this into radians if you want to. Okay? If you want to, I'll show you the formula later, okay? But for now, so that means we're rotating this 180 degrees. So it'll go back to negative 45 degrees. Because that's the correct quadrant that we want. That's the correct argument that we want. Because this is less than 0, right? So that's what we want exactly. Okay? Now, if you get confused, don't worry, let me just show another example on quadrant 3, okay? Now take a look at quadrant 3. In quadrant 3, we have both A, B are less than 0. So both A, B are less than 0. Now since these two are the same, I'll use the green marker as well to demonstrate. Okay, first give you any point. Let's take negative 3 and negative 5i. Okay, for example, negative 3 minus 5i. Okay, now when we plot this, we're going to draw a line, draw a hypotenuse. Alright, clear till here? Okay, so when we draw this, the argument will be where the hypotenuse, so like it will be something like here. This will be the argument, this theta. It will lie where the hypotenuse is, okay? That's where the hypotenuse is. Now we can see that when we take the argument of this, so we get tan, then we already developed the formula, the b upon a, which would be the imaginary part, or the real part. What's the imaginary part here? The imaginary part right here is minus 5. The points, we have to get the points first. The points of this, you remember to get the points before. The points of this are negative 3, negative 5. Okay? Now moving on, we get negative 5 upon negative 3. This cancel, and we get tan of theta is equal to 5 upon 3. Everything fine, right? No. There's something wrong, right? Now it's pretty obvious here, because when you get tan of theta of 5 upon 3, like, wait a second, we get this is equal to tan of negative 1 of 5 upon 3. But isn't this the argument of 3 plus 5i? But there's something right, because then we will be implying that the argument of negative 3 minus 5i is equal to the argument of 3 plus 5i. But obviously this is false. These two are not equal. So once again, to fix this, we're going to have to add pi again to rotate it 180 degrees, and yes, we will have to take the modulus, otherwise we will get a wrong result, okay? Because it will get on the wrong quadrant. In the last example, we took the modulus of negative 45 degrees, the modulus, which would be 45 degrees positive. If we didn't put the modulus, it would be negative 45 degrees, and if we rotated 180 degrees, it would just be on the positive side, which would be the wrong quadrant, which would be like on one of these sides. This is for a greater than 0, and we wouldn't want that, okay? So what we're going to do is, we're going to have to add this. We're going to have to add pi, and where pi and this is equal to 180 degrees, because when we rotate 180 degrees, the side changes. Remember to put the modulus, okay? To ensure that you're shifting the quadrant correctly, okay? Understood? So that's why the formula will be the same, okay? So yeah, let's go ahead and derive the formula right here. Okay? Okay? So yes, in this case, the argument of the complex number z, it will be pi. So let me write pi plus the magnitude of tan negative 1 b over a. And you might be thinking, why are we adding the modulus in this side? The thing is, we don't have to add it in quadrants 1 and 4 because they'll already give the correct result, the positive. Because A is positive, so we get a positive result, like we wanted. Like I showed in the first example when we started to prove the argument. Okay? So this will be the general formula, okay? For quadrant. So this is the general formula for quadrant 1, 2, 3. Now quadrant 4, I'm going to use a red marker because quadrant 1 and 4, quadrants 1 and 4 are the same, okay? Alright? So yeah, let's find the argument here. And remember, this symbol means principal argument. Okay? So yeah, after I finish proving the arguments for these 4 quadrants, I'm going to show you why an argument is multivalued. It's a short proof, but I'll show you the general form of it. For now, let's focus on quadrant 4. Now, we have quadrant 4 here, okay? Take a close look here. Let's say, give me any point, okay? Give me any point. 5, okay. Let's say 5 minus 3i, okay? 5 minus 3i. Okay? So now, let's just join the points again. Okay? To make the triangle. Now, we have a right angle triangle. And where will the argument go? Where the hypotenuse is. So it'll be right here. This is where it'll be. Alright? So yeah, this is where the principal argument will be. Okay? Now, once again, we already proved the formula, so we can just plug it in. Tan of theta is equal to the b over a, opposite over adjacent. Where's the opposite? The opposite will be where the, right here. Opposite of this is this. And the adjacent is right here. Adjacent, this is opposite. Clear? Okay. So now, so adjacent to this is this and opposite to this. Okay? Let's plug in the formula, the values. So what is B here? The points here for B. The point for B is negative 3. Okay? Negative 3. Negative 3 over A. What is A? 5. So, yeah. Okay? But the thing is, there's, oh yeah. The thing is, we don't have to add pi because this is fine. That does it look something similar to quadrant 2? Yes. In quadrant 2, it's flipped. A is less than 0, B is greater than 0. Okay? Here's another example. A is less than 0, B is greater than 0. And in this case, A is greater than 0, but B is less than 0. In this case, A is less than 0, but B is greater than 0. Alright? So yeah, that's what's happening. Because in this case, we would have to add pi, because if we didn't add pi, look, we know that negative 3.5 is also equal to 3.5, right? Right? Yeah. So if we, so like, when we find the argument of this, if we didn't add pi, like if you had to find the argument of instead of 5 or negative, not my 5 minus negative 3, we had to find the argument of negative 5 plus 3i. So we'll just plug in the formula for quadrant 2. We will get tan of theta would be equal to b over a, okay, b over a, which is equal to where's b? B would be negative 5. Negative 5 upon 3. Okay? But this is for quadrant 2. And if we found the argument of this same, of the different complex number, and if we found the argument, in this case, 5 minus 3i, we would get, oh, 3 minus. Oh, that's it. Yeah, so what happened is, there's another, yeah, that's a big deal also. Okay. So let's play one. Oh, sorry, my bad, not that. derivative. Yeah. Okay, let's go on. So yeah, because we can also write this as 3.95, and there's a difference that this, if you plot the complex number, this should be the reciprocal. So if we have like something like the argument of a complex number, negative a plus vi, and we have another complex number, argument of a minus vi. These two are reciprocals. These two will be reciprocals. What I mean by that is when we find the argument, we see the tan negative 1. It's like in this case, it would be tan negative 1. Tan negative 1 of the imaginary part, b over negative a. And in this case, it would be tan to negative 1 of b negative b of the imaginary part, or the imaginary part over the top. Yeah, there's a thing here. We have b upon negative a. We know that b of negative a, b upon negative a is equal to negative b upon a. So that's why in order to shift the quadrant, we have to add pi to this while taking the modulus to ensure we don't get a wrong result. Understood why we do that? So that's why. Wait, did I do something wrong when I found the argument of negative 5 plus 3? Yeah, I think so. This is the general rule. So that's why we have to add pi. Alright? Alright? Okay. Oh yeah, wait. So in this case, we're finding the argument of which complex number? 5 minus 3r. And suppose in quadrant 2, we found the argument of like minus, wait, we found the argument of minus 5 plus 3r. Now we would get that the argument would be tan negative 1 of imaginary part over real part. Look, we're getting the same thing here, but it doesn't matter where the negative sign is. This is 3.5, but we can just shift this here. So this will be tan negative 1 of negative 3.5. But these two should not be equal. That's why we are adding pi. To this. We're adding pi to the modulus of this to ensure that, okay? Because as I mentioned, the tan function, it works between the range of negative pi and 2 radians to pi over 2 radians. Because it only works when the real part is positive, okay? So that's why. We don't want this to be equal, so it's that pi. That's the thing. Okay? So yeah, I just corrected that. So that's why we have to add pi to it, okay? And with the mods. Understood? So back to the my mouth is drying. Okay, just finish this video up. Alright, so where was I? Yeah. Quadrant 4. We're having, yeah, so this would be tan of negative, wait, hold on. Yeah. So in this case, tan of theta would be imaginary part over real part. So we will get tan of theta to be negative 3.5. That would mean theta would be tan of negative 1 of negative 3.5. And like explained, if we used the opposite sign of this in the quadrant 2, we would also get the same result. But we would have to add pi with the modulus to ensure that we have to shift the quadrant correctly, that we shifted the quadrant correctly. Okay? But in this case, we don't have to do anything because this is fine. So this is just the principal argument, okay? Because this is fine. We only have to shift that one, so this cannot be equal. If we shift both, if we shift this also, then, like if we shifted that, If you shift this, then this will be equal to that. We don't want that. We only have to shift 1. Okay? So that's why we shifted to quadrant 2. Okay? So this is the general formula. No modulus, no need to add pi. This is the formula. So we can derive the general formula of this as the argument is equal to tan negative 1 over 8. Yeah, there's no mistake. When I made the argument with the 4 uncomplex numbers, I made a video where I showed the formulas, but I didn't prove it. And I forgot to add the modulus for quadrants 2 and 3, which is very important. So I'm glad I caught that and I'm able to prove it, okay? Because proving things is always good. Because when you prove things, it just becomes lots more fun. Let me use a green marker here. Okay? Try to. Okay? So if you have any questions, let me know. Okay? Only one more thing. I have to prove that the arguments are multivalued. Oh yeah, I have to prove that the arguments are multivalued. Okay, look. Suppose we're finding the argument, and it could be any quadrant. Okay? Like suppose we're finding the argument, usually the argument let's start with quadrants 1 and 4. When you check the quadrants 1 and 4, the argument would just be tan negative 1 of b over 8. This is the principal argument. Okay? But in fact, it is multivalued. Why? Because actually, it's also, this is plus 2 pi k, where k is a positive integer, and k, it could be any, so 10 negative plus or minus 2 pi k, where k is a positive integer and k is multiple of 2. Okay? Because the thing is, let me explain why. Adding 2 pi would mean rotating. Look, we know that pi upon 2 is 90 degrees. So we multiply 4 on both sides. This means rotating plus or minus 360 degrees. We know that rotating 360 degrees clockwise or counterclockwise would still land us on the same number which we originally were on. And if we use multiple, it wouldn't matter. Because like if k was 1, we'll just run it two pi times. It'll be a full circle. We would land the same number. And if we just use suppose we use 4 pi. 4 pi would just be 720 degrees. Yeah. And that means we're just rotating that number 2 times. We'll still land on the same number. Okay? Same goes with the fourth argument. This is for both. This is for both first and fourth argument. Similarly, if you have to find the argument of arguments 2 and arguments 3. For both of these, it would also be the argument it would actually be yeah. So we would also have to add, it will be 2 pi k. It will also be 2 pi k, okay? That's the thing. Because rotating 360 degrees or a multiple of it would stand us on the same number. Same for the negative degrees. Now look, this would be 2 pi k plus or minus pi plus the minus of tan of b over 8. Same like that. Same thing. Same thing except for adding this. 2 pi k. And you can simplify 2 pi k plus or minus pi will stay like this. Because whatever the argument to here, if we add it, it doesn't matter what's the quadrant, you'll just add the same number. That's why the argument of a complex number is multivalued. Okay? but you can try any number of compass to. If you rotate 360 degrees, counterclockwise or just anti-clockwise, you will have the same result. Similarly, if you rotate by multiple of 360, like 720, etc. Okay, so that's why. And yeah, once again, all these conditions apply to quadrants 2 and 3 as well. Okay, multiples, positive integers. Okay, so we can add or subtract. It doesn't matter. You land the same number. But usually, the reason why we use principal argument is because the principal argument always gives one argument. If we had multiple arguments, it would just be messy. But the argument is also multiplied, so it doesn't matter. Alright? So yeah, I think that's. So yeah, guys, I hope you enjoyed this video. This is my whiteboard. I hope you enjoyed this. It's good. Okay. And yeah, I hope you enjoyed this video, and I hope you enjoyed this. I hope you understood everything. I hope everything is clear. All this, the arguments, why they're multivalued, how they work, proof, okay, and why we have to rotate. And yeah, because each function, because another reason, yeah, one more important reason is that the sine function, the sine, cosine, and tangent functions are periodic. This means that if we rotate it, okay, I think we should talk about the polar form in the next video. We'll discuss polar form also, we'll prove it also. But time is very low, so yeah. That's gonna be at pi. 2 pi t actually. Right? So I hope you enjoyed this video. Because the tangent function is periodic. Because if we add any multiple, if we rotate 360 degrees or negative 360 degrees, we'll land at the same result. That's why, okay? So I hope you enjoyed this video. If you have any problems, let me know. How am I now? Oh yeah. Peace out.